Okay, so we're going to continue talking about hypothesis testing where we're comparing two population means. In this case, we are talking about the situation where we don't know the population standard deviation. This is a much more normal situation than knowing the population standard deviation. There we go. Okay, let me get my laser pointer up. Okay. Um, so we're looking at scenarios where we've got independent samples from two populations, neither of which we know the standard deviation for. Uh, we've got to meet the following criteria. All all possible samples have to have an equal probability of being chosen, so it's a random sample. The samples are independent, population standard deviations are unknown, and the sample size has to be at least 30 or both population distributions are approximately normal. So fairly standard set of criteria that we have to meet, pretty much the same as we talked about last time with other hypothesis testing or um, margin of error calculations where we don't know the population standard deviation. And very similar, except for that criteria right there, to set situations where we do know the population standard deviation. Um, there's a couple of different scenarios within this. If we can assume that the population variances are equal or approximately equal, then we can pool the variance. Or if we can't make their assumption that they're equal, then we cannot pool the variance. So there's some slight calculational differences depending on uh, whether or not we can pool the variance. How strongly we think we can assume that the variance is going to be the same for the populations we're looking at. Um, so as you might guess from what we're showing here, we're going to be using uh, the t statistic for this, the student's t distribution. Um, so we're rejecting the null hypothesis if for a left-tailed test, if the t statistic is less than or equal to the negative um, critical t sub alpha, greater than or equal to t sub alpha for a right-tailed test, or the absolute value is greater than t sub alpha over 2 for a two-tailed test. So pretty much the same set of rejection criteria we talked about previously. Just restating our criteria. So if we can meet all the criteria we talked about just a couple moments ago, then we can use this handy dandy equation for calculating our t statistic. You'll note this looks almost identical to the equation from section 11.1 for calculating the z statistic. Again, we've got the difference between our sample means and the difference in our presumed means that from the null hypothesis. The only difference is we're using the sample standard deviations here instead of the population standard deviations. The other gotcha here for our t distribution, we've got two possibilities for degrees of freedom, right? We've got however many samples we had in population 1 and however many samples we have in population 2. As we saw in section 11.1, those don't necessarily have to be equal. So we've got degrees of freedom. We can base that off of either of them. The convention and what's going to give you the most conservative answer is to use whichever is smaller. Okay, so let's go through an example. We have a CPA firm that claims its clients receive larger tax refunds than its competitor. So they randomly selected 15 clients from their firm, and they found a mean tax refund of 942 with a standard deviation, and again, this is going to be the standard deviation of that sample of 103. Their competitor, they got a random sample of 18 clients and found a mean refund of 898 with a sample standard deviation of 95, and they want to test this at the 0.05 level of significance. In order to do this, because those sample sizes are less than 30, we're going to assume that the population distributions are approximately normal so that we can proceed. So first off, what's our null and alternative hypotheses? Well, let's call the clients from the firm making this claim population 1 and their competitors' clients population 2. They want to show that population 1 received larger tax refunds than population 2. So there we go. It's mean population 1. It's mean tax return size. It's greater than population 2. This is our alternative hypothesis. As we saw in section 11.1, we can rearrange this so that the means are on the same size, and we've got the difference being greater than 0 as our alternative or research hypothesis. Right, so that is that line there, H sub A, alternative hypothesis. So the null hypothesis, the logical opposite of that is that difference is going to be less than or equal to 0. Okay, which distribution and test statistic do we want to use, and what is the level of significance? We're looking at a difference between population means. We don't know the population standard deviations. Because the two firms are located in different parts of a large city, it's specified Chicago. It's probably not a good assumption that the variances for the two populations are equal. So we're going to assume that the variances are not equal. Test statistic for unequal variances is appropriate. We're going to test the claim at the 0.05 level of significance. Let's gather our data. There was our sample means, our sample standard deviations, and our sample sizes from the problem. So this is the t-statistic when the variances cannot be pooled, so we've got them separate there. If we plug in our values, so from our null hypothesis is that this difference, the null hypothesis would be that this difference is approximately 0 or less. So we'll have a 0 there. Then we put in our sample means, our sample standard deviations, and our sample sizes. And again, we do need to be careful that we are keeping sample 1 together, sample 2 together, and samples 1 and 2 in the right order here. When we do that, we get approximately 1.266. So looking at drawing our conclusion and interpreting the data, we need to come up with the rejection region to determine the critical t-value. So we need to find the degrees of freedom. And again, we've got two possibilities. Had a sample size of 15 and a sample size of 18, so 14 or 17 degrees of freedom. 14 is the smaller, so we'll go with that. We had a 0.05 level of significance. So that is a t-statistic, critical t-statistic of 1.761. Since 1.266 is less than that, It doesn't fall in the rejection region, as you can see here. There's our critical t-value, and there's our calculated t-value, and this out here is our rejection region. So there isn't enough evidence to support the claim that Smith's clients have larger tax refunds on average than Jones and Company's clients. We can also do this in the calculator. We want to select the two-sample t-test here, two-samp t-test. In this case, we're giving it statistics to input. It's a right-tailed test, so we want to choose the greater than a, I don't know, a tilde over 2. Okay, so this is a font. Please ignore the font that didn't load correctly. That should be a mu, as you can see here, greater than mu over 2, or greater than mu 2. So your test is that mu1 is greater than mu2. Population mean 1 is greater than population mean 2. Looks like we've got something going on here with the fonts again. They must use a special font for the calculator input here. So you're telling it what this bit of gobbledygook is saying is that you want to choose they've got an option to pool or not pool your variances, and we're telling it not to. Then highlight calculate and press enter, and it gives these results. So there's the t-statistic, the associated p-value. You can see that that is greater than our critical p-value, our level of significance of 0.05. We'll give you the sample standard deviations and sample sizes and sample means again. P-value is 0.1079, which is greater than 0.05, so we fail to reject the null hypothesis. Okay, the other option is equal variances. If you can assume that the population standard deviations are likely to be equal, and we've got independent random samples, and the other criteria, sample size of at least 30 or normal population distribution, then we get this test statistic where we've got pooled deviations. So your numerator here looks exactly the same, difference in means minus presumed difference in population means. The pooled variance down here, we've got degrees of freedom times degrees of freedom from sample 1 times the standard deviation from sample 1 plus degrees of freedom of sample 2 times standard deviation of sample 2 plus divided by sample size plus sample size minus 2. It's kind of like a sum of degrees of freedom, if you want to think of it that way. Square root of that mess times the square root of 1 over the sample size of 1 plus 1 over the sample size of 2. It's a bit more, it's a bit of a longer calculation. There's a bit more to do. The other thing to note is the degrees of freedom we use for our t-distribution is this, sample size 1 plus sample size 2 minus 2. That's our degrees of freedom in this case, instead of the smaller of the two. It's kind of a pooled degrees of freedom now. All right, so let's look at this. We've got a home improvement warehouse that claims that people interested in completing their own home improvement projects can save time by attending its workshops. So I can go to Lowe's or Home Depot and attend their how to install tile workshop and know what I'm doing when I retile my bathroom. Um, so they claim that people attending the tiling workshops take less time on average to complete a project than those who don't. To test the claim, they randomly selected a group of 10 people who attended the workshop and surveyed them about the time it took to finish their tiling projects. So our total sample size is 10. Um, people in, oh, okay, so sorry, this is one group. People who attended, 10. This is probably going to be population 1. So this population spent a mean of 14.1 hours completing projects. The sample standard deviation was 2.3 hours. They talked to another 10 random people who probably bought tiling supplies there. Didn't attend the workshops. They spent a mean of 15 hours with a standard deviation of 2.4 hours. That's fairly similar. And they want to test their warehouse's claim at the 0.01 level of significance. Okay, we're going to assume that the variances are equal. The population variances are equal but unknown, and that the distribution of times to complete the tiling projects are approximately normal for both populations. Otherwise, our sample size of 10 is too small to proceed with this type of statistics, and we'd have to do something more advanced that we're not covering in this course. So let's state our null and alternative hypothesis. Population 1 will be those who attended the workshop. Population 2 will be those who did not attend the workshop. The Improvement Warehouse's claim is that people who attend the workshop spend less time on their tiling projects on average than those who don't attend. So what we're looking at is the mean time spent on the project. We think that those who attended the workshops spent less time than those who did not attend the workshop, so mean 1 is less than mean 2. That's our alternative hypothesis. We can rearrange this so all the means are on one side, and that gives us mean 1 minus mean 2 is less than 0, right? Because if mean 1 is smaller than mean 2, we'll have a negative number. And so we can state those hypotheses as, here's the one we're proposing, that mean 1 minus mean 2 is less than 0. The null hypothesis is the logical opposite, is that that difference is greater than or equal to 0. All right, so what distribution to use, what test statistic to use, and what's our level of significance? Okay, we're looking at the difference between two population means. We don't know the population variance, but we're assuming it's equal between the two populations. They're independent random samples. We're assuming the population distributions are approximately normal. So we're using t-test for equal variances. The level of significance given was 0.01. So we can gather our data. We've got means of 14.1 and 15, standard deviations of 2.3 and 2.4, and sample sizes of 10 in both cases. Again, the population variances are assumed to be equal, so we're using the test statistic for equal variances, which is this messy looking thing. Again, that is our degrees of freedom for this test statistic down here. So if we input our values, we've got the population mean from 1, population mean from 2, sample size minus 1, sample size minus 1, standard deviation 1, standard deviation 2, sample size plus sample size minus 2, sample sizes again, and again this comes right from our null hypothesis, that the difference between our sample means is in the null hypothesis greater than or equal to 0. This gives us approximately negative 0.856. So let's look at what this means. Um, we're looking at a left-tailed test, so we want the t-statistic to be less than the critical t-statistic in the rejection region. So our degrees of freedom is 10 plus 10 minus 2, or 18. If we look at that with the 0.01 significance level, that gives us a critical t-value of negative 2.552. Negative 0.856 is much greater than negative 2.552, so we do not fall in the rejection region and we fail to reject the null hypothesis. Visually, that's like so. So there's the 1% significance level, critical t-value here. This is our rejection region, and we are up here. So we cannot reject the null hypothesis. There's insufficient evidence at the 1% level to say that people who attend the tiling workshops take less time to complete the projects than those who do not. Again, we can do this in the calculator. So this is a left-tailed test, so this we need to select the mu less than mu1 less than mu2, right? This right here. Select that. Choose yes next to pooled. It shows up fine here. Interesting. Highlight calculate, hit enter, and we get our p-value. So again, we could take the t-value it spits out here and find the critical t-value, or we can just look at the p-value here and say that yes, that's greater than our significance level, so we failed to reject the null hypothesis. So again, it's essentially the same calculation we've done, or very similar calculations to everything we've done before. It's a little bit more complicated in that we've got the pooled and not pooled variance versions of it. The pooled variance is really the new and different part, but very similar conceptually. I want you guys to all remember that these are essentially it's the same algorithm each time. We're doing the same set of steps. It's just variations on it, and the hard part is figuring out the right variation to do. And we'll move on to, that's it for section 11.2. We'll move on to something else next week.